Hello students, in last lecture we had seen the proportional allocation where in proportional allocation Ni is directly proportional to Ni. Means from large data take large number of observations. Here we will going to see the Neyman's allocation. Here Ni is directly proportional to NISI. We will going to prove this one. So under Neyman's allocation, Ni is directly proportional to NISI means from large strata take large number of observations, and from a strata having larger variation take large number of samples. So definition of Neyman's allocation is like this. An allocation is called Neyman's allocation if Ni values are selected such that variance of Y/St is minimum subject to the condition that total sample size N is fixed. Means here Ni values are obtained. Ni means sample size from ith strata. These Ni values are selected such that variance of Y/St should be minimum and subject to the condition that total sample size N is fixed. So this is the definition of Neyman's allocation. Look at this theorem. Under Neyman's allocation, prove that Ni is directly proportional to NISI. Also obtain an expression for sample size from ith strata. First we have to prove Ni is directly proportional to NISI, and after that we have to find the expression for small ni. So to prove this one, Ni is directly proportional to NISI. Proof of this theorem. Ni is found such that we want to find Ni such that the definition of Neyman's allocation is Ni values are selected such that variance of Y/St is minimum. First condition is variance of Y/St is minimum, and second condition is total sample size N is fixed. So total sample size is summation I is equal to 1 to k Ni is your small n, and this is total sample size. This should be fixed. So here we want to find Ni and some conditions are given. We solve this problem by method of Lagrange's multipliers. We solve this problem by the method of Lagrange's multipliers. So here we want to find Ni. For that Ni, variance of Y/St should be minimum, and one condition is the total sample size should not be changed, it is fixed. So in Lagrange's multipliers we defined some phi. So whatever we have to minimize right here, variance of Y/St we have to minimize, and plus lambda is constant of Lagrange's multipliers, and this summation Ni is equal to N is fixed means write this as summation I running from 1 to k Ni minus N. We already know variance of Y/St is formula for variance of Y/St in terms of Ni. So put that formula, which is 1 upon n square summation I running from 1 to k ni into ni minus small ni si square upon ni plus lambda into summation I running from 1 to k ni minus n. In method of Lagrange's multipliers, we define this phi and then we take derivative of dou phi by dou ni, derivative of this phi with respect to ni, and equate it equal to 0. We find the value of ni by using this dou phi by dou ni equal to 0, this equation. And for that value of ni, variance of phi bar st is minimum, and summation of ni is equal to n is fixed. So consider dou phi by dou ni. So apply derivative here, derivative to this phi. So this will be 1 upon n square dou by dou ni of summation I running from 1 to k ni into ni minus ni si square upon ni plus lambda into, so dou by dou ni will be here, dou by dou ni into summation I running from 1 to k ni minus n. Now we cannot take this derivative directly inside this summation because this derivative is partial derivative with respect to ni. So there are other terms also, means there are n1, n2, ni minus 1, ni plus 1 up to nk. So this derivative is with respect to only ni. So all other values of ni are constant. So to simplify this 1 upon n square dou by dou ni, first simplify this summation. So put I equal to 1, this will be n1 into n1 minus n1 s1 square upon n1. Put I equal to 2, this will be n2 into n2 minus n2 s2 square upon n2 plus 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 up to, put I equal to I, then this will be ni into ni minus ni into si square upon ni plus put I equal to k, then this will be nk into nk minus nk into sk square upon nk. So we had to solve this summation plus lambda into dou by dou ni of, we cannot take this dou by dou ni directly inside this summation because there are other terms also. So solve this summation first. So this will be n1 plus n2, sum here it is ni plus 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 up to sum here it is nk and this minus n. So next step will be take this derivative inside the bracket. So after taking this derivative inside the bracket, this will be 1 upon n square dou by dou ni of n1 into n1 minus n1 s1 square upon n plus dou by dou ni of n2 into n2 minus n2 s2 square upon n2 plus 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 up to, take this derivative here. So this will be dou by dou ni of ni into ni minus ni si square upon ni plus up to dou by dou ni of nk into nk minus nk sk square upon nk plus this lambda plus lambda into, take this derivative inside the bracket, so this will be dou by dou ni of n1 plus dou by dou ni of n2 plus up to dou by dou ni of this ni plus up to dou by dou ni of this nk minus dou by dou ni of this n. Now look at here. Here derivative with respect to ni, there is no ni, so this quantity is constant with respect to this derivative. So first term will become 0 because derivative of constant is 0. This quantity is constant with respect to derivative with respect to ni. Here also there is no ni, so this will again 0 plus up to all terms up to I minus 1 will be 0. And if we take derivative here, look at here, we can write this as dou by dou ni of, solve this term, take this inside the bracket, and this will be ni square si square upon ni minus. If I take this ni here, then this will be ni, and if I take si square ni inside the bracket, then ni will get cancelled. This will be ni si square, right? Plus up to all other terms are 0. Plus lambda into, now derivative of this n1 with respect to ni will be 0 because n1 is constant. Here also it is 0. So all other terms are 0. Only here it will be 1. So derivative of this will be 1 plus up to 0. And here also there is no ni. So this n is constant with respect to this integration, this derivative. So this will be 0. Alright. So next step will be like this, 1 upon n square. So here, if we take dou by dou ni here, then ni square si square is constant, and the derivative will going to apply only for 1 upon ni. So derivative of 1 upon ni is actually minus 1 upon ni square. So this first term will be minus ni square si square upon ni square, because derivative of 1 upon ni is minus 1 upon ni square. And if we apply this derivative here, then this will become 0 because there is no ni. So first term will be like this, and second term will be plus, here it is 1 means here it is lambda. So this is dou phi by dou ni. So consider dou phi by dou ni equal to 0 because we have to equate this equal to 0, and we have to find the value of ni from this equation. So after equating this equal to 0, this will be, after equating this equal to 0, this will be ni square si square upon n square ni square equal to lambda. Now send this ni square in this side and lambda here, so this will be, now ni square will be now ni square si square upon n square lambda. Taking root, after taking root, ni will be ni si upon n into root lambda. Now here capital N and root lambda is constant, because capital N means population size and lambda means constant of Lagrange's multipliers. So we can write this in proportion. So this will be, we can write this as Ni. We can write this in proportion, so Ni is directly proportional to Nisi. So this is we have to prove. Ni is directly proportional to Nisi. So first part of this theorem is Ni is directly proportional to Nisi. Also obtain an expression for sample size from ith strata. So we have to find expression for small ni. Now this means from larger strata take large number of samples, and from a strata having larger variation take large number of samples. Look at, give the number to this equation. Suppose this is equation number 1. Take summation over I running from 1 to k of Ni on both sides. So take summation over I running from 1 to k on both sides. Then we will get, now here 1 upon n into root lambda is constant. So this will be summation I running from 1 to k Nisi. We want to find value of root lambda, because lambda is constant and we have to put here. So from this, you know summation I running from 1 to Ni is small n is equal to 1 upon capital N into root lambda summation I running from 1 to k Nisi. Take root lambda or multiply both sides by root lambda and send this n in this side. So this will be root lambda is equal to 1 upon n summation I running from 1 to k Nisi. So put this value of root lambda in equation number 1. So equation number 1 implies Ni is equal to Nisi. Equation number 1 is Ni is equal to Nisi upon n into root lambda. Root lambda is this one put here, so this will be 1 upon n summation I running from 1 to k Nisi. Solve this further. So here capital N will get cancelled and we can write this as Nisi, rewrite it. So this will be summation I is equal to 1 to k Nisi, and this n will be multiplied to this quantity. So this is the expression for small ni. This is the expression for small ni in Neyman's allocation. Now we can write this formula in terms of Wi also. So how to write this formula in terms of Wi? In right hand side, divide numerator and denominator by capital N. After dividing numerator and denominator by capital N, then this formula will become, here it will be capital N, here it will be capital N. So this will be if we divide the equation, suppose this is equation star, the equation star by n, if we divide the equation star by n on numerator and denominator, then we get, and what we get, if you divide here by n, then this will be wi si and this will be wi si. Then this expression will be like this: ni equal to wi si upon summation I running from 1 to k wi si into n. So this is the formula for ni in terms of wi. This is the formula for small ni in terms of ni, means ith strata size. Thank you.